Thanks for the introduction, and thanks for inviting me, of course. I'm Lucas from EPFL. That's the title of the talk. Let's jump right into it. So, an overview for today's events. We're going to talk about protocol security vaguely at a very high level, just to sort of refamiliarize ourselves with the context. I'm going to nail my theses to the wall and complain a bit about UC for a couple of slides. And about how the proofs that I write using UC aren't very good. And then we're going to get into the meat of the talk. I'm going to give a somewhat self-contained introduction to state-separable proofs. So if you haven't seen those or heard of them before, that's fine. Then we're going to talk about using them for the setting of protocol security. That's sort of modular protocol security. That's sort of the name of the framework that I've developed using those. And then at the end, we'll have a big example proof using MPS for an actual protocol. Simple one, but an actual one. So, protocols. Before protocols, we have games. This is back in the prehistoric ages. So games are usually used to analyze things in a sort of standalone setting. So you have some kind of individual scheme you're trying to analyze, and you're sort of looking at it as like an algorithm in isolation. So is this encryption scheme secure? Does this signature scheme work? But you're only considering a scheme sort of in isolation as like an algorithm you're trying to analyze the properties of. And the usual way you model security is something that looks like a game. So the adversary sends messages, receives answers, and they're trying to sort of break some aspect of the scheme. For example, maybe forging a signature after querying a few examples. In the protocol setting, things get a bit trickier because now instead of having sort of one scheme in isolation, you have multiple parties interacting together. And what makes things really tricky is that the parties don't have to follow the algorithm anymore. Some of them can be malicious. And that's really sort of what separates the wheat from the chaff here. So the red party here is marked as malicious and can do whatever he wants, which makes things a bit more difficult. But you can still sort of squint and see things as a game if you model things correctly. So all of the malicious parts that a given party can do, those become sort of interaction points for the game. And then the black parts, which are the honest parties, that's sort of like an algorithm you're trying to probe. So there's a sort of natural connection between game-based or standalone security frameworks and protocol security frameworks that you can reduce the setting of analyzing the security of a protocol to that of analyzing the security of a game, albeit a very complicated one. And so there are different flavors of making this kind of reduction. The most common one is UC security for universally composable, which tries to provide some nice guarantees. So we'll talk about that very briefly in theory. So if you abstract away from all of the details, you get a very common sort of paradigm, especially if you abstract away from the adversary and sort of use a dummy adversary kind of notion. So the basic idea is that on one hand, you have the actual protocol execution on the left here. And on the other hand, you have the sort of ideal situation. So in the ideal execution, instead of the parties actually sort of interacting, you have a trusted third party which does everything magically for you. And basically, the interfaces between these two protocols are going to be different because in one you have actual messages to send and the other one you don't. And so to emulate what the malicious adversary thinks it's able to do in one protocol, you have a simulator. And the idea is that the simulator interfaces with the trusted third parties, and, well, just the one trusted third party, or the ideal functionality as it's sometimes called, and is trying to emulate what the malicious party can actually do in the original protocol. And the idea is that anything that you could do in the actual protocol to break stuff, if you can sort of emulate those effects in the ideal situation, that means that any attack is sort of an attack against the ideal protocol, which is sort of almost by definition secure, because almost everything that's important is done by the trusted third party. And so this kind of simulation notion is very common even outside of UC security. So it's not about this notion exactly, but rather the details of how this thing is formalized. What matters in practice when you're writing proofs is what exactly do we mean by a simulator? How do we specify what happens in a protocol? How do we glue protocols together if we can do that? And that's sort of where my personal issues with UC come into play. So personally, when I say my criticisms, it should be somewhat self-directed. Like I'm not saying UC is bad, I'm saying when I write proofs in UC, I feel bad about my own proofs in like these ways. So often there's sort of a gap between the specific formalism that you'd get from UC after reading the paper and what proofs actually look like. So the paper talks about interactive Turing machines. I don't think I've read a proof that talks about literally writing stuff to tapes, and though in theory you need to do that, right? So there's a bit of a gap there. A gap that's somewhat formalized, and there's some papers that sort of bridge the gap in a bit more formal way, like the one with Lendl and all, where they sort of formalize a higher level version of UC, but I digress. And then another sort of criticism I have of proofs that I end up writing in UC is that often the specification for the protocols is somewhat vague. So it's even a bit above pseudocode, where often it's more like a prose kind of description. First, this party sends this message to all parties. What does it mean to send to all? Does it mean that you sort of have to wait until they receive it? There are many sort of details like that are often left vague. And then the simulator is often given as like a high-level strategy. It's like, okay, well, the simulator is first going to do this, and then he's going to do that, and then the simulator is going to wait until this happens. And you have this sort of vague notion of what exactly the simulator is doing, and also whether or not they're sort of allowed to do the things they're doing, and also various notions of like timing sort of get swept under the rug. One sort of mistake you see often, not really a mistake, but one thing you see often in simulator proofs in UC is that they assume that the adversary has like a causal strategy. The adversary is going to first try and attack this way, and then that way, and then that way. Often this shows up when you do protocols with rounds. They'll assume that the adversary is going to attack the first round, then the second round, then the third round, and not try and like do the third round first. And so the simulator is going to be, okay, I simulate the first round, then the second round, then the third round, without actually proving that you can ignore the order. So I digress. And the simulators you get are often very complicated because you're making a big step at once. You're saying, okay, I have this real protocol and this ideal protocol. I'm going to make a big jump using this big simulator all at once. And so often you have like just one single step where you just write one simulator. Maybe you do hybrid proofs to show that the simulator works, but it's still a big bundle of logic you have to deal with all at once. And also, it's often unclear how to use standalone security notions in the UC setting. So let's say I have a signature scheme that's secure in the standalone setting. Can I use the fact that I know that to say something about a threshold signature scheme that tries to generate those kind of signatures? It's a bit trickier to do that than you might think. And often, like if you have a sort of framework, a concrete framework for doing game-based proofs, then you're sort of in interactive Turing machine land if you try to formalize it. So there's a kind of gap in the connection there. So let's go back down to standalone security, because I think there are good solutions we have with the advent of state-separating proofs. And so you have similar issues initially, notions of vagueness. It sort of happened initially when we were doing game-based security, but then eventually we developed pretty rigid pseudocode for defining games, and that helped solve a lot of these issues. And then I think another sort of issue with standalone security that was recently resolved with state-separating proofs is making very commonplace things like writing reductions much more fluid, and also making it so that you can reason about games in a very modular fashion. So let's talk about state-separating or state-separable proofs. So this is the big introduction, and we'll sort of go over it completely. So let's lay the backdrop. We have what we're trying to model as a game, as we sort of mentioned at the beginning of the talk, and an adversary interacting with the game. And so the example we should keep in our minds this whole time is we have two games. The adversary is trying to figure out which one they're playing against. So maybe in one game, for example, like if you look at encryption, the way you'd model it is in one game, the adversaries get challenge encryptions of their messages, they get ciphertext backs, and they're actually encrypting the messages they're sending. And the other one, they're always encrypting random messages, and the adversary shouldn't be able to tell between them. That's sort of a running example you might use. So the basis of this is that you need a way to sort of define games. And then often the way you'd prove security is you sort of say, okay, well, the adversary can't distinguish these two games together, and you'd appeal to some sort of reduction. So you say, well, this other game is secure, and we can show that, we can transform an adversary A for this game into an adversary B for that game, et cetera, et cetera. The way you sort of try and do things with state-separating proofs is a bit different. So instead, you say, okay, this game is too complicated. Let's break it up into smaller components. So you break up this big game G into different components that you glue together. We'll talk about what gluing means later. And then what you're going to try and do is you're just going to say, well, I know by assumption or by sort of what I'm reducing to that each of these components is like similar to something else. So maybe just one of those components is the same as something slightly different. So I can swap out that component for something else. Then I can glue stuff back together. Then I break it apart in a different way maybe. I swap another piece out, etc. And so I'm slowly transforming my game until I reach the target game that I want to get to. So instead of having sort of a big hop that you sort of have to reason about and do stuff inside the proof itself, you have very small hops, and you try and sort of say, I'm going to do a little bit at a time, and this is sort of encapsulating the hybrid technique for game proofs. So that's sort of the high-level idea. Let's get into the details a bit more. So I've been talking about games, but with state-separating proofs, you have a sort of a generalization called a package. So a package, you can think of it as a game, except that it also has input functions it depends on. So a game provides functions that an adversary can call. A package is the same way. It provides some functions that can be called, here f and g, but it also has dependencies, here h. So this game A provides f and g, but also depends on a function h. And a good way to think about this, if you've done any kind of programming, is like a library. A library has certain exports. It can export some functions, but it can also import functions. And the idea is that if a library imports some function from a module, if you used a different module, it would still work, might behave a bit differently, but it would still, compile, right? And so here's a common form of pseudocode used to describe this game. You have some state that can be modified. Usually you write that at the top. So we have one variable x, which is sort of modified each time you call one of these functions and then used. So then when you call this function f, you pass it in an input, and that gets added to x, and then x gets modified. And the second function g will return h of x, where h is a dependency of a. So maybe that's a hash function, maybe it's something else. And that will return h on whatever x happens to be at that moment. So there's a kind of state being kept by the package. And so the most basic thing you can say about two packages is that they're literally the same, and that all their code is basically functionally the same. So this is sort of this triple equals thing, which is a very strong notion of equality. I won't really formally define it, but you can find details about this. So here I'm saying these are equal because z is basically always x minus 1. And the way y affects z is the same, and the difference is in g, where I have to add 1 to z to get the equivalent behavior as if I were doing h of x. So just an example of what equality looks like. And you just define this to be able to say these things about the different gluing operations that we use later. So this is an equality relation, symmetric, transitive, et cetera, et cetera. So let's get to the first way you can glue packages together, which is really the meat of this framework. So this is the first way you can glue stuff together, which is horizontal composition. So basically, if I have a package A, which has some inputs, and a package B, which provides those as outputs, I can glue them together. And what this means semantically, it's as if you have two modules in software, and one of them imports the other one. So now it can call the functions in that module. And if that module has some imports on its own, well then now the sort of thing glued together is going to have those inputs. And so this is a very useful notion because you can sort of separate out part of a game into another game you've already sort of reasoned about. So that's very useful. One property of this kind of composition is that it doesn't matter the order you compose things in. So if I have 3 games that I want to, or packages that I want to compose together, I can glue the first 2 and then the third one, or I can glue the last 2 and then the first one. And as long as I connect them in the same way, it doesn't matter. So it's like a circuit, It doesn't matter how I slice it up. So that's very useful. The way you sort of formally say this is using the triple equals. So there's a sort of associativity notion you have here. And then the second way you compose packages together is vertically. And so what this signifies is that if I have 2 packages, I can just put them side by side and I can interact with both freely. The states don't interact at all. Each package has its own state, which doesn't just touch the other one. And I can interact with any of the functions that either of them provides. So it's sort of like if I have 2 software modules, I can put them into one big library, and then I can use any of the functions provided by either of them. And this also has a notion of associativity. So it doesn't matter the order you stack things together and how you group them. In fact, it's also commutative. If I stack things this way or that way, up to sort of ordering of the functions or their names, it doesn't really matter. The important part is just what functions are provided. And that's sort of encapsulated here. Does it matter? Oh, yeah. So one thing that's pretty crucial is that you have a nice interplay between horizontal composition and vertical composition. Basically, it doesn't matter as long as there's no sort of usage between in the sort of crossway. For example, here A doesn't use anything that D provides, and B doesn't use anything that C provides. So there's nothing going across. And if there's nothing going across like that, it doesn't matter how you glue things. So I can first say, okay, I'm going to put A and B on top of each other, C and D on top of each other, then I'm going to glue these things together like this. Or I can glue the top halves together and then place them side by side. And so often you just implicitly use this because you're sort of, you're saying, I'm just gluing stuff together at the beginning, and I sort of don't really care about the order, and it's well defined because nothing sort of cross interacts. Another little gadget you need is 1. So the notation here is that you have 1 and a set of functions, and the idea is very simple. It's just a package which re-exports a function that it imports. So here, 1 of f exports a function f, which when called also calls a function f as an input. So basically, it's just sort of a way of re-exporting functions, and it's more of like a technical detail. And one property of 1 is that if I put 1 in front of a or behind a, it's sort of the same as having a. So it's more used in a bit of a technical way. For example, one thing you might want is that I have one package here. I want to put something in front of it, but I also want to export some of it as well. So if I just have one thing in front of it, whatever this guy exports is what's exported. By having a 1, I can sort of move stuff through. So now we get to adversaries. So the usage of packages is a nice generalization of games because we can also use it to define adversaries. So an adversary is basically a package which has some inputs based on what game it's trying to play, and the output is either 0 or 1 in sort of a randomized way. And so that's basically back to sort of the running example. The adversary's guess as to whether or not it's in the first game or the second game, more or less. And you use this to define sort of a notion of advantage. So basically, if the adversary is trying to distinguish G and H, then it should behave very differently between them. So it should return 0 very often in one and not very often in the other. If it always returns 0 in both, then it's not very good at distinguishing the two games. And so there's this notion of difference, which also satisfies this nice additivity property. So if I want to look at the distance between two games, it's always going to be less than sort of going via a third game. And so this is what lets you sort of accumulate hops, basically. So we use this notion of adversarial distance to define two stronger notions of equality, or rather a bit weaker in the sense that they require less of the games to work. So the first one is just the usual notion of equality. Here we consider all adversaries regardless of their power. So they can be unbounded in computation. And we say that the adversary can't distinguish through games at all. And this is useful for capturing notions of like perfect statistical security. So for example, like maybe there's two identical ways of sampling from a distribution. For example, maybe you XOR two random variables together, that's the same as sampling just one of them. And this would be well captured by the first notion of equality because there's no difference whatsoever in the distributions. But it's sort of good at capturing more subtle notions where like you combine different states together and whatnot. And the second notion, which is used to capture computational assumptions, here you restrict yourself to adversaries that have a bounded amount of computation. You can define this more formally, of course. And then also you have a sort of wiggle room epsilon. So the advantage can be small, but it can be non-zero. But it has to be sort of bounded, usually by some other sort of game. So this is where you get reductions from, for example.
So you have, how are you distinguishing between statistical security and perfect security?
So one thing I haven't put in the slides is that at the bottom, you're taking a different adversary class. The adversaries have to be bounded computationally. It's an important sort of subscript there.
So what you're saying is the top one, when in your description was A was from an unbounded class.
Exactly.
The bottom one you're saying A was from a bounded class, but you could also have the bottom one from an unbounded class, then you get statistical security.
Yeah, you could do that as well, of course. If you want statistical security with some sort of gap, you could do that. But usually, yeah, so for example, like some things, if you were, for example, to appeal to like Schwarz-Zippel or something like that, it would be in the bottom class technically. But usually, basically either you're saying, there's sort of three kinds of statements you usually make. One is, these two things are the same. The other is, well, this thing is improbable because of statistics. So like, this collision can't happen in a random oracle. And the third thing is like, we have some assumption. And we're appealing to that via the epsilons. But yeah, good point. And so then, the secret sauce that makes this all work is the fact that all of the notions of composition respect equalities. So let's say I have G0 is approximately the same as G1 up to some epsilon. Then if I have a vertical composition of A with G0, I can swap out G0 for G1 and get something that's approximately equal even in the composition. And then same for horizontal composition. So if A uses some stuff in G0, I can swap out G0 for G1, and I get A using G1, and that's approximately the same thing. And so this is extremely important because this is what allows you to do this sort of modular reasoning. So the strategy you're going to take all the time is you're going to take a big game, you're going to decompose it, you're going to take one part, you're going to hop over to another part, you can glue stuff back together and sort of rearrange stuff via qualities, then you can break stuff apart again, maybe horizontally this time, you do another hop, et cetera, et cetera. And each time you do a hop like this, you're basically accumulating one epsilon that you can all add together. So if I need to reduce to 3 different games, I'm going to sort of separate out that game, 3 different times and then make the hop. So let's see an example. We're going to look at algorithm encryption. Like with both the examples today, the point isn't to convince you of the security of the scheme, because I think telling you that algorithm encryption is secure is not big revelation. It's more to give you a flavor of how these kind of proofs work. So the exact details aren't super important. It's more sort of just getting a feel for how this stuff works. So first, what's the assumption we're going to make for security? Well, it's computational Diffie-Hellman. So this will probably look weird if you're used to the usual way these games are formatted. So the usual way you might think of CDH is, okay, well, I get some input as the adversary, which is going to be the points A and B, and then I need to give a point C, which is going to be AB times G, where A, B are the discrete logs of A and B. So here we have this sort of challenge thing, which is sort of like that, except we have this B equals 0 and. So basically this is sort of a trick. What's happening in the 0 version of the game is telling us whether or not we won. It's saying, okay, yeah, you guessed correctly, or you didn't guess correctly. In the 1 version of the game, it's always going to tell us you didn't guess correctly. And so this is going to be useful in a bit, because basically when we switch from 0 to 1, we can't win, ever, in essence. We can never guess correctly when we're in the 1 version of the game. So saying that 0 is approximately the same as 1 is saying that we can't guess correctly, in essence. We'll see how this shows up later. But yeah, so keep this game in mind. So then, encryption, we're going to look at sort of standard NCPA. To simplify, we just have a version where we can query this challenge function once. And to sort of summarize OGML encryption, the basic idea is your public key is A. And then to encrypt, you're going to pick a random B. You're going to do B times A. That's your sort of shared secret in Diffie-Hellman. You're going to give the commitment B times G as part of the ciphertext. You're going to hash B times A to get a symmetric key that you can then use a standard encryption scheme E with. And so the game that's being played is that the adversary sends a message M0, and then in one version of the game, they're going to get that message encrypted. In the other version of the game, they're going to get an encryption of a random message instead. And so basically, if they can distinguish an encryption of a random message from encryption of their chosen message, then that's bad. And here we model the hash function as a random oracle. So we have a table, and if we have a point that's not on the table yet, we sort of generate a random value for it, and then we return whatever the table says at that point. So security analysis, well, first of all, we're going to say we start with NCPA, and we say we're going to separate out this sort of elliptic curve stuff and move that into the CDH0 game. And so we can do this because the CDH gives us A and B as the 2 inputs, and then we need to guess the challenge C. A becomes our public key, and B becomes the nonce commitment that we use for the ciphertext. And so the question is, how do we do the key? Because basically, the key needs to be the hash of C, or AB times G. So what we do is we basically program the random oracle in a sort of way that's an implicit consequence of this formalism. So basically what we can do is we say, since the key is sampled at random, it doesn't really change anything if we happen to check in this hash function whether or not we met the challenge, because it's just a random value. And so if the adversary happens to hit upon this point C, they're going to get this specific key K, well, which is a random value like any other entry in the table. And it's this specific key that we're going to use to encrypt. So basically, we're going to always encrypt with whatever the hash of the challenge is going to, the sort of target A times B is going to be, even if this game in the middle doesn't really know what that is. And so here's the big trick, is that since we've moved CDH0 out, we can swap to CDH1 and get an epsilon. And when we swap to CDH1, this condition, if the challenge succeeds is always going to be false. Because by fiat, the CDH1 version of the game just says this challenge is false, I'm never going to let you win. Which means we can sort of eliminate that if condition, and then now we just have a key that's generated and used to encrypt, and so we can inline it. So now we have a key that just generated right before we encrypt the ciphertext, and then we encrypt using that key. And then at this point we can inline all of the elliptic curve stuff because we don't need CDH anymore. So we generate A and B ourselves, and we just give them to the adversary. And so at this point what we're doing is we're generating a random key and encrypting using that, so we just need to appeal to the security of the encryption scheme. And so we do this by extracting it out. So we have some notion of basic insecurity, not even CPA or CCA, just one-time encryption. So you could even use like a one-time pad. That would also work. And we basically appeal to the fact that this is emulating exactly what the sort of end game should be. Basically, instead of encrypting ourselves, we just defer out to a game. And we have this equality here. And so if you put everything we've seen so far together, you get this chain of equalities. So we start at NCPA 1, 0. We sort of decompose CDH out. We do a hop to CDH1. We re-glue it back together. We separate N0 out. We do a hop to N1. And then we sort of do everything back in reverse. And so then you get epsilon2 once and epsilon1 twice. So if you were to sort of write this out, you'd say that NCPA of El Gamal is equal to 2 times CDH plus 1 times end of the encryption scheme. So that's what state-separable proofs look like in a very simple example. If you want more examples, you can read Mike Rozelek's excellent derivative cryptography book, which I highly recommend. And so now, hopefully that wasn't too challenging, we're going to talk about MPS, which is using SSPs for protocols. So far what we've done is we've sort of defined a framework for packages and talking about how to glue packages together, how to compose them, and then how packages can be used to model security. And what we'd like to do at this point is use packages to model protocols. So there's a few steps we need to do to get there. The first is that we need a notion of sort of asynchronicity. The reason for that is that often when you're defining the logic of protocols, sometimes you think about it like, let's say you want to interact with a player of the protocol as like a sort of package. One problem is that their answer might not be ready yet. Maybe they're waiting for somebody else to send them a message. So they need to tell you, okay, I'm not ready yet, call me back later. So you need some kind of notion of asynchronous execution so that when you call a function in a package, it can say, oh, I'm not ready yet, call me again. So I'm not going to formalize that here because it's sort of a bit technical, but you can use sort of any kind of async await notion in programming language. So like one very simple way to imagine it is just the function can return either, yes, I'm good, here's the answer, or I'm not ready yet, call me again. And then you have sort of chains of awaits. So a function itself might call another function and say, oh, if the function returned I'm not ready yet, I'm also going to return I'm not ready yet. So you have these propagated chains of asyncs. So, and also, like in the example I'm going to give, like all of the awaits are going to be implicit. So it's just sort of a technical detail. Then from there you need to get to what I call systems. So this is sort of a notion that I thought was no more necessarily earlier when I was formalizing this stuff. It's sort of less necessary now, but one thing you might want directly is a way to send messages to other parties in a protocol, just as an inherent notion of the framework. And so a system is basically a package where you can also send messages to other packages. And it's basically the same logic as packages, except you have this new operator, times, which is like vertical composition, except you have message passing. And so the idea is a message, each blue arrow here is a channel where you can send multiple messages on the channel. And the way it works is that, the way you formalize this is that when you read from a channel, essentially that's sort of calling an async function as a dependency. If the channel has a message ready for it, you get it. Otherwise the channel says, okay, it's not ready yet, you need to wait. And then the package itself is going to say, okay, I need to wait to the person calling it. It's not extremely important though. So we can get to protocols. So the way you define a protocol in MPS is via packages, or systems technically. So each of these systems can send messages to other systems, and it has potentially asynchronous functions. And the usual setup is that a protocol consists of multiple packages, one for each player. So you have a static number of players, and a package representing the ideal functionality. And implicit here is that each package is going to have some dependencies on the ideal functionality, representing the functionalities they need to use, and also some outputs, more than one potentially, representing the ways that they can be sort of activated. So very often it's just going to be a single function which says run the protocol, but maybe you have multiple points of execution. Maybe there's 2 ways to start the protocol with different inputs. Maybe you have a setup where you can sort of have different stages of a protocol. Maybe you separate it out into 3 functions, 1 for each round. So that would give you then multiple output functions here. And then furthermore, a protocol is also defined by what parts of the ideal functionality leak outside. So here this red arrow represents the fact that there's one function in the ideal functionality that the adversary can call directly. And so this represents the adversary being able to cheat or getting extra information about the execution. And there's 3 kinds of composition we're going to see. The first one doesn't involve protocols. It involves a protocol and a game. So protocol, I'm using this script notation to separate from games which use plain text. And so the basic idea is maybe the ideal functionality itself has dependencies. So one reason this is useful is, let's say the ideal functionality is using some kind of computational assumption. Maybe it's using an elliptic curve or something. Well, then it's going to be useful to say, actually, this elliptic curve stuff is part of a separate game. And the sort of thing I'm foreshadowing is that if once you separate out a game from an ideal functionality, you can use a hop. So that's the utility in saying, I'm going to compose a protocol with another game. And this game itself may continue to have dependencies. And so you can compose it more and more and just add more stuff to the ideal functionality. That's one form of composition. The other form involves 2 protocols. And it's sort of the analog of vertical composition, but for protocols. And what it represents is that I have a protocol that now has one big ideal functionality, which is F and G composed vertically, and has the leakages of both. And then I also have more players. So here I'm composing a protocol of 3 players, another protocol of 3 players. The end result is a protocol of 6. And the idea is that each of these protocols is sort of operating independently with an independent state, and I get one big ideal functionality for both of them. This is more useful when combined with the following, which is horizontal composition of protocols. So this one is a bit more esoteric. So the setting here is we have 2 players here in the first protocol P, and they're using some functionality which isn't defined necessarily by an ideal functionality, but by other code. This might make more sense if you take like a programming point of view. If you're writing a complicated MPC protocol, you might have a separate library for like a sub-protocol. Like maybe I'm doing MPC and I need oblivious transfer. Well, I'd have separate code for oblivious transfer that I call into. But this is code and not an ideal functionality. So you can sort of separate out what's happening as I have code to do MPC and then I have code to do oblivious transfer. And the code to do MPC uses the code that does oblivious transfer. So that's the sort of idea you're trying to capture here. Run protocol uses the code of another protocol as a sort of sub-functionality or sub-protocol. But it's not ideal in the sense that there's actual code running here. And so one thing you want for generality is that each player can use potentially multiple players in the sub-protocol. This is convenient to have in general, even though in practice it's usually just one-to-one. But very importantly, you require that each player in the sub-protocol is used by exactly one of the players in the main protocol, because otherwise you have like issues. So here, for example, P1 uses Q1 and Q2, and those are the 2 ones that it controls, and that's it. And because of that, P0 can't use either of those. So it has to use Q0 only. And that's a very important point. And the ideal functionality becomes F and G together. So the adversary can see the leakage from both F and from G. And they need to be together to both basically supply this information to both Q and P. And basically, formally, P1 gets sort of merged with Q1 and Q2 as one system. P0 gets merged with Q0 as one system, and that defines your sort of protocol. So those are the 3 types of composition you have. So next, when we define security, what makes protocol security harder than standalone setting is, of course, the fact that you can corrupt people. So we need to define what that means here. The idea is that some of the players are going to not behave correctly and going to deviate from the protocol specification. So yeah, okay. So the basic idea is, let's say P2 is malicious in this setup. Well, what's going to happen is that all of the sort of output arrows become sort of useless, because the idea is the adversary doesn't want to follow the code. What they want to do is they want to sort of interact directly with what P2 is able to interact with and try and deviate to gain advantage. So here P2 has one way to interact with F directly. And the idea is that the adversary now gains that as a direct capability. So they don't have to follow the protocol code in P2 anymore. They can directly interact with whatever resources that P2 uses. And if you had channels between P2 and say P1, well, then the adversary could send along those channels as well. But usually it's just a matter of saying what ideal functionality stuff does P2 use. The adversary now gains access to those. And basically you have, and what you need to do is you basically need to sort of specify which parties are corrupted and in what way. So one downside of MPS is that it's sort of restricted to the static setting. So dynamic corruptions or adaptive security aren't sort of handled by the framework because you need to change which set of parties are corrupted dynamically. So that's a weakness of the framework. And the most basic form of equality you can have with protocols, you're saying, well, when I look at, oh yeah, something I forgot to mention is that if I look at this box on the right, it's a game, basically. It's a big package defined by all of these things interacting together, but at the end I have some parts that are honest that the adversary can call, and I have some parts that are malicious that the adversary can call. And it's a big package they can interact with. And so basically by choosing a corruption model for who's corrupted and how, I go from a protocol to a package. So it's an important point to note. And so the most basic form of equality statement I can make about protocols is saying, well, given a corruption model, when I compile them down to a package, the packages are the same. So for most protocols, this is not going to be the case because you need some kind of simulation to make it work. But if you have, for example, trivial changes in the ideal functionality, this kind of relation will hold. But because this doesn't hold without simulation, we need to define what that is. So simulation is a pretty simple idea. Before I marked some arrows as red as sort of malicious and some black arrows as honest. The basic idea is that the simulator can touch the malicious parts and change them, exposing the same interface, and maybe even sort of hiding a different interface. But the honest parts have to go through with a big 1. So the honest parts the simulator can't touch at all. Otherwise, it would just be trivial because then the simulator could just do everything in its head and completely ignore what it's using. So the interplay between the malicious parts that the simulator can touch and the honest parts that have to go through is what makes security hard, and it's a very important thing. And so what you define is this notion of simulated instantiation at the top. So given a corruption model in a simulator, I can define this big package where I have this simulator placed in there and I glue everything together in the right way. And so the usual notion you use is a notion of simulation which is directed, hence the arrow instead of an equality. So just because P sort of is simulated by Q doesn't mean the other way holds. And you have an epsilon because you can have a computational assumption. And what this is saying is that there's a simulator such that the instantiated package, just of a plain one, is equal to the instantiated version of the other package, but with the simulator helping this reduction to hold. And importantly, there's no mention of an environment because this is sort of implicit in just how everything's defined. This package, basically this package has to have the simulator embedded into it, regardless of what the adversary does. So because of the order of definition, this one package with the simulator already stuck and well-defined and concrete and not changing has to sort of work for all adversaries. And so that's why you get this sort of composition notions, because you sort of define the simulator before the adversary, which is equivalent to the environment in UC. And so then, for the 3 types of composition we've seen, they have great properties. So if I have 2 ideal functionalities or just packages, and they're approximately the same, then if I glue them onto a protocol, I can make the hop to the other one. If I have 2 protocols, one is simulated by the other, and I have 2 protocols composed horizontally, I can make the hop to the other. And then if I compose protocols by having one protocol use another as a subprotocol, I can swap that subprotocol out. So this is a very similar kind of setup that you had in state-separable proofs, but now in the protocol setting. So it's sort of a natural extension of the things you were trying to achieve there. So proof strategies. So one advantage of the framework, or disadvantage depending on how you look at it, is that there's many ways to do a proof now, because you have all these ways to decompose protocols together. And then when you're doing protocol security, it's about games and SSPs. So then you have all the tools available to SSPs to do your proof, in addition to the modularity you've gained here. So you almost have like 2 dimensions. So one new thing you can do that's not very common in UC is, I haven't mentioned ideal functionality as like a thing you simulate to. In MPS, it's protocol to protocol. So it's one protocol simulated by another. One advantage of this is that you can do multiple hops. Instead of saying I have a protocol, then I go to an ideal functionality, I can make pit stops. I can say I have a protocol, I can make a hop to another protocol, to another one, and then finally my end destination. So in the same way that you can do game hopping for standalone security, you can do protocol hopping for protocol security. So I can have intermediate protocols I define just for the proof, and that don't really need to be defined outside, and I sort of use those to make my life simpler. So one sort of diagram illustrating this extra freedom is that you have the real protocol at the top, this line. You have the ideal protocol at the bottom, this blue line. Your goal as a sort of cryptographer is to get from the real protocol to the ideal one. One strategy you can use is you can just make a big simulator that does the jump. So that's one strategy. One way MPS can help you is that the simulator, since it's appealing to the logic of SSPs, can be broken down. And you can do this with hybrid games, of course. So I can make multiple hops to make this big jump easier. But what you also get in MPS is I can go horizontally via protocol hopping. So instead of doing the original protocol all the way to the ideal protocol, I can make a pit stop and move horizontally. And as I move horizontally, I have less space to cover vertically. That's sort of what I'm trying to illustrate with the diagram. Yeah, so hybrid arguments are like the vertical direction. It's basically taking a big simulator and sort of decomposing it piece by piece, or arguing that it's correct. But you can also decompose the protocol in the other dimension. So I can, instead of...
The hybrid, you could say that this protocol is made up of this protocol and often...
Yeah, so what you can do is you can try and do decomposition via ideal functionalities that you can do. But one thing you don't see a lot in proofs is saying, I'm going to invent a protocol just inside of this one proof for the sake of making it easier. Instead, usually the hops are always going to be the ideal functionalities that are fully defined in the paper as a big thing. There are things that it's possible to do, but it's sort of less. It's sort of like there are things that are like idiomatic in programming languages, right? And so this kind of protocol hopping style where you write very small steps between the protocols you're trying to simulate isn't really the convention because it's sort of hard to do that. You need to explicitly write out ideal functionalities for each of these things. Whereas here, it's sort of like when you do game hopping in SSP, you have many intermediate games that are just throwaways. You use them once. Here you can have protocols that are throwaway and you use once, if that makes sense. We'll see an example where we'd actually do protocol hopping, so that might help clear up some sort of what the difference exactly is. So I guess we'll get the example next. So the example protocol is a very simple one. The idea is that you want to sample a random number between a group of parties that's unbiased. And a simple way to do that is you have some kind of group where you can add stuff together. So for example, bit strings in XOR, that works as well. Or a field where you add the field elements together. And the basic idea behind the protocol is everybody commits to their contribution. Once everybody's committed, they open their commitments, and then they sum everything together. That's going to give you an unbiased result, because everybody's had to submit their contribution before seeing anything else. So first step, we need to define the protocol. So this is sort of the notation I'm using. We have the name of the protocol at the top. So normally there's sort of n parties. Here this is a general protocol, but I'm defining them all the same way via this one sort of package, because their code is all identical. All that changes is their index I. So I ranges from 1 to n, and all that changes is basically which functions they're calling, because they're all behaving symmetrically. So I need one of them. But you could also, in general, have protocols where each party does something different. That would be possible as well. So often in OT, you might have this, because often the two parties in OT behave differently. And on the right, we have our ideal functionality fcommit. And once again, the details aren't super important, but the basic idea is that there's an extra S there that doesn't matter. But basically, you first commit to a value. It's going to set what xi is if it hasn't been set yet. Then you can wait for everybody to commit, and that's going to sort of block the protocol. It's going to say, I'm not ready, until everybody has committed. Then you can open, and to open, you have to actually have committed before. And it's going to say, OK, now the package remembers that you're opened. And then you can wait for everybody to open. And then you receive all the messages that have been committed to. And so the protocol that uses this ideal functionality, the way it works is that you generate a random value, you commit to it, you wait for everybody else to commit, you open it, you wait for everybody else to open, and then you sum everything together. So simple enough. And there's no extra leakage here beyond what the adversary can use because they corrupted certain parties. And the ideal function protocol, rather, is this. So basically, you have, at the start of the protocol, you need to synchronize. So this is sort of another downside of NPS, is that as defined currently, you need to emulate the round count because the adversary can tell the fact that a protocol has a certain number of rounds because they can sort of delay it a certain number of times. So at the start, you need to sort of reflect the fact that you had this commitment phase, and you need to sort of synchronize. And synchronization is basically sort of like commitment, except you have no value to provide. And then after doing this sort of synchronization phase, they get a random value which has been generated in advance. And so you have a shared random value between everybody that's unbiased. And so our goal is to get from this protocol to that protocol. And so we're going to use another sort of proof strategy. So the way we're going to set it up is that when we instantiate P, we have sort of two sides. We have the honest side that the simulator can't touch, and we have the malicious side that the simulator can't touch. And then we have the ideal functionality, which is there. And the basic idea is what we can do is we can start adding some logic in front of the malicious part, because that we can touch. And we can even change the ideal functionality as long as the behavior of the whole thing is the same. And then eventually, we're going to have a big simulator. And we're going to say, actually, well, this is the setup for saying that P is simulated by Q. So we can get rid of the simulator and call that a hop and then start over again. So to illustrate, here's our basic setup. So on the right, we have the honest parties, or on the left, rather, we have the honest parties with whatever their code is. It's the same as before. And on the right now, we just have what the adversary can do. And what the adversary can do is basically all the things that the party has direct access to. So the adversary can call the commitment functionality, the wait commit, open, and then wait open. And the sort of convention I'm using here is that I denotes honest indices. So when I say rand I, that means sort of all the honest parties, and K denotes the malicious parties. So K ranges over however many parties are malicious. And fcommit is sort of unchanged. And so here, the adversary has control over several malicious parties, so they get commit K for each of those Ks. So we're going to make one hop based on just this package stuff. So we're in package land right now. We're going to make a hop. So what's the hop going to do? It's basically going to allow parties to say, actually, I don't have a value to commit to. I'm going to let you generate it at random for me. And this changes the ideal functionality in the places marked in blue. So now when you set a value, once again, I've got to have this typo S, so we can ignore that. But basically, it says, if you have a value to provide, I'm going to set xi to that value if it hasn't been set yet. Otherwise, if you didn't provide a value, I'm going to generate it at random for you. And so obviously, by having the honest parties, instead of generating it at random, let the functionality do it, that doesn't change the behavior of the thing as a whole, because we're just moving some code around. And then we add this extra sync I variable, which is reflecting the fact that xi has been set. And so this obviously doesn't change the behavior either. And then for the malicious party, we sort of just need to rename these functions. So when we do commit, we instead set k using our x value. And instead of waiting for commit, we wait for set. So that's one hop. Next, we make another hop. So here, what we're doing is we're saying, when we do wait open, before that give us all the messages. Now we're going to make it so that wait open gives us the sum. So for the honest parties, instead of summing it themselves, they let the ideal functionality do it. That's fine. The issue is that the malicious party, they expect to see all of the individual messages. So we need a way to sort of emulate that for them. So we add this function, leak. And what leak's going to do is it's going to check if that party has opened their value yet, or if that party is malicious. And if so, they're going to give them their contribution alone. And the idea is that for malicious parties, they can see their contribution immediately. And for honest parties, the malicious parties need to wait for them to actually open, which is what we want. And so basically, to emulate the fact that they saw all the contributions before, they now call leak on each of the individual parties, which is what the dot denotates. And basically, at this point, we have a simulator on the right. This gamma2m is basically a simulator over this new functionality. So what we're going to do is we're going to throw that simulator away, because basically we're simulating a protocol P0 that I've just defined here for the sake of this proof. So we've gone from our initial protocol, and we've just shown through our sort of arguments that it perfectly is simulated by this one. And so this is just all the code we've sort of seen so far, and all the changes we've made. And so the advantage of defining this intermediate guy is that all this simulation logic that I've just defined here in the right, I can throw that away. I don't need to remember that anymore. I've sort of made a checkpoint. It's kind of like if you're trying to beat a big boss in a video game, if you can save in the middle and come back, it's easier. So here I have a checkpoint, and I can sort of continue from there, and that reduces the complexity of the simulator by a bit. So we do what we did before. We unwrap this, and we have the honest parts on the left, the malicious parts on the right, and we have all the functions the malicious guys can access. So the extra thing is now leak, because that's the thing we added to F1. And so then we make our next hop. So what's this hop? The basic idea is that what we want to do now is that we want to sort of eliminate the ability of the adversary to set an extra value. Because before, the honest parties would sort of let the functionality generate a random contribution for them. The malicious parties would have some contribution that they wanted to have. Here we're going to make it so that instead all of the malicious parties have to sort of give one contribution together, and there's no individual contribution for each of them. And so the way we're going to make this work is we're going to allow the adversary to cheat with one delta value, and at the end, the sum that they're going to get is the sum of the random contributions plus this delta value. And so then what the simulator is going to need to do is they're just going to need to sort of fudge the set k thing so that it basically preserves this sum. So you can sort of check the math here, but the basic idea is that you want to sort of add these contributions into this delta that you're going to use once all the malicious parties have contributed. And so that's going to represent the sort of offset they want to add to this random value. But you also need to subtract the leakage so that the sum works out. But otherwise, so once you look at this sort of sum of j plus delta, you're going to get the actual delta that they're sort of contributing there. But the point is that you simulate that out. So then the next hop is basically, at this point, we can sort of eliminate the leakage. Because the leakage is just giving us random values for each of the honest parties, and then the final value. And so generating random contributions for each of these parties, we can do ourselves. And so what we do here is we just have logic. All this simulator is doing is it's saying, each party that I need to get the leakage of, I'm going to generate a random value, except if it's the last of the honest parties. Because if it's the last honest party, I need to make sure that the sum is the same as the one that the ideal functionality is going to give me. So I just choose their specific share so that the sum is the same. So basically, you're just trying to make it so that the sum of the random contributions you've given is equal to the random value that you get from the ideal functionality. And so that gives you this F2 thing. And at this point, we say, OK, we have another protocol that we've gotten to, and we separate out into a synchronization part, and we tensor that with another ideal functionality for this randomness part. And so this randomness, basically, it samples a random value, and we can cheat by having a delta before we see the random value, and then we see alpha plus delta at the end. And so then what we do is we have a very small thing left, is we just say, well, this F3 is the same as just ignoring the delta, because you have to contribute the delta before seeing alpha, so it's the same as just ignoring it, because the distribution is going to be the same. And so then we use the fact that if F3 is equal to something else, well, then this protocol, I can swap F3 out for something else. And that gives me the ideal randomness functionality. So that's the proof. So that shows the different things you can sort of use. So some sort of takeaway conclusions about the framework. I think precise pseudocode is a good idea because having a well-defined pseudocode sort of makes everybody agree on what's happening and what different things mean, makes it easier to check proofs. And it's a necessary step if you want formal verification. You need a well-defined semantics so that you can actually write things down for a computer to understand, right? I think in its current state, the pseudocode is a bit crufty, and there's a lot of sort of things that are like very obnoxious to write, which could be much simpler. And so I think an even higher level of pseudocode is sort of needed for this kind of framework to gain traction. Having the ability to bridge with games is nice. So at the end there, we did a little hop where we just appealed to sort of a standalone security of a package. Having that kind of thing is very nice. So you can do things like saying a threshold signature that produces a signature from a specific scheme is secure because that scheme is secure in the standalone setting. And because you're sort of using games for the standalone setting to define protocols, you have a natural sort of bridge between the two. So it's useful for that. This is sort of a niche thing, but if you want to make statements like this thing cannot reduce to this other thing, you need a very well-defined meaning for what a reduction is. Because if you don't know what exactly reduction is, it's going to be very difficult to prove that a reduction is impossible. And so basically by having well-defined formalisms and foundations, it becomes easier to make these kind of meta-statements like this reduction is only possible if you have OT and stuff like that. And that kind of thing is actually interesting to NPC folks usually. They want to say, oh, To do MPC, you need, one sort of prolonging question is, what exactly do you need to do MPC, right? So a good, big result would be proving that if you don't have XYZ primitives, you can't do MPC at all. And this kind of statement requires very precise formalisms to make. So reasoning about large games is very hard, even in this framework. And that's where I think formal verification can help a bit. One thing you saw at the end is that even in our DO protocol, we had this extra synchronization round. And that's sort of an artifact of the framework itself. You can sort of get around it if you give the simulator the ability to delay messages even in the honest parts. That's sort of the root of the issue here, is that the honest parts, they can't touch at all. And so to enable this kind of timing artifact to disappear, you need to be able to sort of delay messages on the honest part, even if you can't see what they are. And modularity is, I think, a very good feature, and even if it's sort of present in other frameworks, the style proof that you write in a sort of modular way of thinking is a thing you sort of want to get more practice at. So hopefully we see more works embracing that in the standalone and protocol setting. And then finally, this is a big thing. It's kind of a pain to typeset. So that might be a big blocker too. So it's a bit annoying to write out these big games in LaTeX. And that's it for the talk. Thanks very much.